Mystic River Building Company. I appreciate you taking time out today to come to hear a little bit about energy efficiency and Energy Star homes. Enoch from the Northeast Utilities, who is going to be one of our speakers this morning, has been MIA this week. We heard from one of his colleagues that he's been out with the flu. So we don't know whether he's going to arrive or not. But Andy Gill is our general manager here at Mystic River Building Company, and Andy is a HERS rater and a BPI building analyst. And Andy will also talk a little bit about some of the programs that Northeast Utilities has in relation to Energy Star and that sort of thing. But Andy's going to be doing the PowerPoint presentation for us. At any time during the presentation, if you have any questions at all, Andy will either address them right at that time, or we'll write them up on the board and address them after we finish the presentation, whichever seems to work best. We'll have plenty of time for questions and answers afterwards, and happy to help you any way that we can. So with that being said, I'd like to introduce you to Andy Gill.
Good morning.
Good morning.
Thanks for coming out. I'm a morning person myself, especially Saturday mornings. So the topic of our presentation today is demystifying green. There's a lot of questions I'm sure consumers have about what is green, what isn't green, because anytime you go through Walmart, Stop and Shop, everything's green or environmentally friendly, and it's just so, it's become very convoluted, so we're just going to address that a little bit. So, and I found this picture, and I just thought it was perfect for demystifying green because it's my phone. So what we're going to talk about is green is, if you look it up and get a definition, because I didn't even know what it was anymore. So I looked it up, and what it has to do with is the environment. It's either lowering your impact on the environment, controlling your impact on the environment, or reducing or actually completely eliminating your impact on the environment. But that's not what, and when you see different products, you know, it's, you know, or when you're talking to a vendor or whatever, and they say, hey, it's green, and they say, really? You know, no kidding. Everything's green. So what we have to do is educate ourselves, or put some effort into building science if we're going to talk about green in the residential market, or in our buildings, and I'll address that in 1 second, as to what is green or what is energy efficient, because it kind of splits down the middle. You have the products that you're using, which have they have an embodied energy, and they come from either renewable or natural resources. So the products themselves, such as, and I'll use for example a kitchen cabinet, or like a cabinet such as this. You know, this could have either formaldehyde in it or in the glue, or it could have you know, low VOC or volatile organic compounds, none in it at all. But you buy it one time, it goes in place. I'm sorry? Oh, it goes in place and that's it. That's the impact. But then we talk about other aspects such as insulation and heat loads. Those have actually it just continues to grow and grow and grow. The impact on the environment, the amount of fuel, the fossil fuels, or whatever it is, the amount of energy that you use to heat and cool a home, or, you know, lighting, different things like that. It just grows as time goes on and our natural resources deplete. So that's how I view green, and we're going to go into, as we move forward, we're going to talk more about obviously building and remodeling and the impacts. So this is a breakdown of the energy usage in. But this thing has a really cool pointer, so I'm going to try to use that. And I can go right down here, like this. No, wrong side. This one up here. So our buildings in the United States use 40% of the energy used in the country. And if you look at this, actually I'm going to get rid of that pointer because I can just point at it quicker than that. No, I think you got an email. North?
I think it went downstairs.
Did it? Oh, it's gone? Good. All right. So 40%, our buildings use 40% of the energy, and then transportation 28%, which I thought was interesting and I wanted to show. So what we do, where we live, where we work, and how we get to and from work accounts for about 70% of the energy used in the country. So our computers at home use about 1%. My house is probably a little more. Cooling, 5%. Electronics, 7%. I don't know what wet clean, I researched that. Wet clean, that's actually laundry, because I had no idea what that was, if anybody else knew that. Refrigeration, so, and that's not cooling, but refrigeration, 8%, cooling, 12%, and then we get into some pretty cool stuff here. So cooling, lights, water heating, and heating. Heating is 30%, water heating is 12%, and lights and cooling each 11 and 12%. So that right there is all of it. So heating, cooling, air conditioning, and lights is pretty much the stuff that we really look at when we design a building. Okay. And there's two ways to conserve. I look for a different word to conserve energy or to reduce the amount of energy we use. And the way I see it, there's two ways. And we can change our habits and behaviors, which is very easy to do. I do it every day, which it's not. It's, you know, we get very ingrained in our daily lives and our habits, and it's very difficult to change. But I'm going to put it here for a reason. I want to go back to it. Or we can increase the efficiency by governing the products and the mechanical systems that we put in place. So by design. And I was going to add another slide here, but I didn't get it in time, so I'm sorry. So this is how we can achieve maximum energy efficiency. And I kind of have this is my 5-step process that I go through. So if you call in and we're either looking to build a new home, we're looking to do a deep energy retrofit on an existing home, or we're just going to do some remodeling. We go through the same step, whether it's a high-rise or it's a condo. It's the same exact step every time, and that's by design. So, and we're gonna go break each one of these down. The thermal envelope, distribution systems, consumption, and then we add renewable energy. So a lot of times, I've been in this business for a long time in the energy efficiency business and building, well before it was called green. And I really don't like the word green, but we're going to call it energy efficiency. Renewable energy, if people come to me all the time and say, I want to put geothermal and solar panels on my roof. So if I had a nickel every time someone said that, I'd have like $5. So, which would be fantastic. But renewable energy sources, the panels, that's like end game, and I want everyone to see that there's a process that you go through. So you don't just jump on and throw geothermal in. And when at the end of this, hopefully you'll understand that. If we put geothermal in and then we put solar panels on, you'd be spending 4 or 5 times as much money than if you just followed the process and took the low-hanging fruit and reduced the amount of energy you actually need. And you'd be more comfortable also, which is great. So step 1 would be design. And when we're talking about a new house, a good home performs well and is comfortable and is healthy because it's designed that way. It doesn't just happen. So a lot of buildings are, if you think about when a building is being put together, or if you're doing a remodeling project, or you're doing an energy retrofit, you have all these different products that are being put in. You have all these different subcontractors or people that are installing them, and they need to look at it as a whole house approach. They each need to understand what each other is doing, and not just the HVAC guy, the electrician, the plumber. These guys, they all need to understand what their impact is on the end game, what the expectation of the result is. And so that's what the design or the evaluation, energy audit, all that part. So we need to make a plan, figure out who's going to be involved in that plan, and that they're all working in unison towards the same common goal. So this is, I was going to put a picture of a house plan, but this was kind of a cool, the United States, the EPA, US EPA put this out, and I thought it was kind of vibrant, so I put it in here. Okay, this is the thermal envelope. You've probably heard of this before, or maybe not. But the thermal envelope has a lot of it has a lot of jobs, and we're gonna try to simplify it a little bit. The thermal envelope is simply just connecting the dots, what we're considering inside versus outside. And you say, Andy, I know what's inside versus outside. If I'm inside the house, it's inside. If I go outside, it's outside. But that's not necessarily the way it is. Here, and this is, I have a better slide a little bit further, but just because, if this is the way I'd like to put it, just because you have shingles on it and water stays out of it, or is supposed to stay out of it, doesn't necessarily mean that it's inside. So what we're talking about is the places that we consider heated, that we consider home. So in this particular picture, right, I don't mean to stick my foot right here, in this knee wall, behind here, like they have this drawn here, this outline. This is what we're going to consider our thermal barrier, our thermal envelope. So this little space here, which is inside, is covered by your shingles, and hopefully doesn't get wet. We're considering that outside. Or a garage, we consider outside. They have this, well, we call them bonus rooms before, but now I've been seeing them advertised as frogs, finished rooms over garages. It's a real term. I don't know, I thought it was pretty creative, I wanted to share it with you. But, so, it's cool. Anyway, so that, underneath it's unheated unless you heat your garage. And that space underneath is going to be have a very different feel than over your kitchen, because that's obviously heated. So, well, I think we're done with this slide. We can move on. Okay, so what makes up a thermal envelope or a thermal barrier? Insulation, obviously. Windows and doors. The wood framing materials. Dimensional lumber and plywood. Sheetrock. Plywood. Siding. All of these things. I'm going to go to here because I just want to. I'm left-handed. I'm wicked left-handed, so we're going to. So if we have, let's say this is an exterior wall. Here's the bottom plate. And you have to think about the different layers. So this is insulation here. We'll consider this. Insulation, we have woods. Let's say we have a window, so there's more wood here. There's a point to this, by the way. I'll get to it in a second. I'm building up to it. So this is a wall. This is outside. And this is inside. And I'm going to draw, this is the cross-section view, and I'm going to draw the same wall as if we were to take the roof right off of the house and looking down onto the studs. So, and my point is, so that you have studs 16 inches on center or not, depending on who laid the wall out. So then this is insulation. So now here we can see there's a stud here, stud here, stud here, stud here, and then in here we can see you have a header that's 9.5 inches, and you have two top plates and a bottom plate. So my point being is that there's different paths, and the wood makes up about 22% of your exterior wall. So when you go to Home Depot and you say, "This is fantastic," it's R19. It says so right on the thing, right on the craft face back. R19, I have R19. No, you don't. So it's a weighted UA, but you have about 22% of your exterior walls are made up of wood. About 8 to 13% are made up of fenestration, because we need light in windows. So if you subtract all of that out, and you have different paths, this path would be, let's say it was a fiberglass R19 or foam or whatever. This is one path A, this is path B, and let's say we have a window here. This is path C. So each one of them has a different heat requirement. So when you add it all up and you figure out how much heat you actually need for the house that you live in for the temperature that you want at design condition, which would be each one in this town it's 7 degrees. So they say it doesn't get below 7 degrees. We were in Vegas last week when it did, so thankfully we didn't experience that. But we were at the International Builders Show getting an education. But so anyway. It did drop below zero, and some homes, there was a lot of freezing and things, but it's not very often that we drop below that, and that's pretty much how it works. So I hopefully you can understand that, and if you have questions, please ask them. Anybody want to ask you a question? Good, everybody gets it. This is a picture of. This is an infrared camera. I took this picture several years ago. And when we go into homes, we go into a lot of homes, ranches, 1950s, and you take a picture on a very cold day. You can see all through here, this is cold. This is all cold, and you can see the studs here. And this is actually, see this? This is that light shining against here. So it's not actually warmer. It is warmer, but it doesn't, it's not actually indicative of the experience. This is more here and more so here. So you see that this is this is either missing insulation, or even more so, let's say that there's insulation is put in poorly, and what happens is, there's different pressures within the house, so air starts flowing through from outside, because in the winter it's always windy, and it's blowing through, it goes through all of these different pieces of building materials that we have, that we think of the outside as a monolithic wall. It's all one piece, but it's made up of thousands of pieces, so air finds cracks everywhere if it's not air sealed properly, and then it just convectively flows through and up, and that's what we're seeing here, is air moving through. And we're going to get to moisture in a minute, but what the number one transport of moisture is air. Is the transport mechanism for moisture or water. This is missing or poorly aligned insulation. I put some words in here just to really kind of cue me, but I'd rather just look at pictures. Okay. Moisture is a thermal barrier, thermal envelope, however you want to word it. It has several jobs, but what we like to think about is more insulation and R value and all this. But the number one job a thermal barrier has, or a thermal envelope has, is to keep moisture out. So, and that was the problem that a lot of people, when you go to this high R value wall or high performance wall in the ceilings, you can cause some problems, which we're gonna get to. But the number one job of a thermal envelope is to keep moisture out. And the number one form is bulk moisture. So that would be like flashing on a roof that's done wrong, and it's just water pouring in. Or in the second one, which is the most problematic, is vapor. So, and this is we can see this here. It's not dripping wet. This is vapor. So in order to keep vapor out, we have to air seal properly. We have to air seal the exterior at the outside walls, and we have to seal it up. And then when we build our walls, I'll go back over here real quick. This time we'll use black. There's by code we have to put a vapor barrier on the inside wall. But what we really need to do, and when we design this, is, and we're increasing the amount of the different technologies, different products, and everything. So we have to use our knowledge about building science in general when we're assembling these structures. So if a wall, you have to think of, if this is a vapor barrier here, it means it's not going to dry. So just as important as not letting moisture in, we need to be able to let moisture out, because it'll get trapped in the wall. So in the summertime, we have about 98% humidity outside to 100%, so it's driving moisture from high to low. So it's actually, and you put the AC on, and there's a guy happy in a chair over here, because the air conditioning's on, and it's 100 degrees out here, and you have a vapor barrier on the inside of the wall here. What's going to happen is, if there's fiberglass insulation and it's not air sealed properly, if the foam isn't thick enough where the dew point reaches at a certain point, condensation will build up behind this poly vapor barrier, because we have the vapor barrier in the wrong spot. And then in the wintertime, we want this vapor barrier on the inside. So if you can follow along with me here, the vapor barrier or vapor retarder is on the wrong side of the wall half of the year, no matter what. So what we need to do is we need to actually allow moisture and design these walls and look for it's called permeability. So a class 1 vapor barrier, class 1 is less than 1 perm. Class 2 is I think 0.1 to 1, and this would be 1 to 10, 3. So more importantly, or as important as not letting moisture in, is having the ability to let these building structures dry out. Because if moisture gets in and it can't get out, then now we're talking about rot, decay, mold, mildew, and structural failure, and that's not sustainable or green. So this is just common sense stuff that we need to think about when we're building advanced technologies or buildings. Keep moving. This is a great example of thermal bypass. So in this particular instance, so we're in a 1950s ranch. It's had 4 homeowners. Everybody wanted different lighting, and this is the ceiling of that they put in of that ranch. And then what they do is they put in the recessed lights and they pull out the insulation. They don't put it back. And then we're in the winter. It's in the winter time now, and you have all of this. So it's not a continuous. It doesn't have continuous insulation, and that's just direct thermal bypass. And that's an example of different trades. We think of, we buy a car and it comes off an assembly line, and we know that all those people, we would like to think, all those people are talking, communicating, the electrical people with the people putting the gas tank in and the steering wheel. But our homes are made on site, with concrete, multiple different tradesmen, and they need to all communicate together. And that's a good example of someone, the insulation guy put the insulation in, someone went along afterwards because his job was to put a light in and pull out all the insulation out because the customer wanted lights, but didn't put the insulation back in or even bring up the point that he did so. This is a great slide of, this is an area that I talk about a lot. And in those frogs, finished rooms over garages, and in capes, this is awesome, an awesome picture. I'm gonna use that pointer thing now, because I think it's important. Right here. So we're in a cape, and we've all been in capes. And we put Christmas lights back here, things like that. And you have sheetrock here that goes like this, and you put insulation here, and there's your knee wall. So if this is insulated, this needs sheetrock behind here. This is missing an air barrier right here. So what happens is that cold air comes in and just robs the heat. It starts this convective loop and takes the heat out. The house puts the heat back in. It takes the heat out, puts it back in. So it's just removing heat from your home. So a good design or a good retrofit is either to come across here and ply with this. So it needs to be 6-sided. So if you think about a cereal box, a good thermal barrier is much like a cereal box. If you remove the front of it, all the cereal is going to fall out. Same thing in a good thermal barrier. You need to have sheetrock, plywood. You got a stud, top plate, bottom plate. So and that will keep, and it needs to be air sealed. That will keep the insulation in place without air moving through it, and the insulation will work as it's supposed to. But this is a very, very common problem, and this causes. Here's another one right here actually. So you have heat coming here and frozen pipes in bathrooms on the second floor. This is one of the main causes. Is in a rim joist, it's not sealed properly. The rim joist being between. We're standing on the floor here, and there's a floor system below us. So and then typically not in this building, but typically there'd be a sheetrock underneath that. So in between those two areas is a space. It's about a foot. And if you go follow the floor joist out to the outside wall, that's called a rim. That's called rim joist, and we have to seal that, insulate that, and create a barrier. Because what happens is the cold air just comes in, goes right over, finds your bathroom pipes, freezes them, and breaks them. So you need to have a sealing, you blocking, sealing, stopping airflow from coming inside it.
You need to be concerned with a moisture trap in that cavity. You have to have it vented.
In which
With that
cavity?
cavity that you have pictured there.
Behind the knee.
Right here?
That opens the void there.
This piece right here?
No, behind the
Behind the knee
behind
wall.
the
He
knee.
wants to know if that needs to be
Right where your
done.
arrows are.
Right here. This would.
Yeah, does that become a moisture trap?
No. Well, it could.
Or do you use
It depends. It depends on how you're approaching it. If you're going to use foam, and if you're going to use foam, or depending on the area, the building official, the high density cellulose, your exterior walls are no different than your roof, and we don't vent our walls. So if you stop the air from coming in with air impermeable materials, such as high density foams, or even half-pound foam that's thick enough so you don't have a dew point problem, then no, you don't need to vent it, and that's called an unvented roof assembly or a hot roof. But if you want to vent it, see how they have this space here between here and so this is air ventilation going through here and going so it comes in through the soffits, air comes here, and then it goes out through the ridge here. So you could vent it, and this would be open to this ventilation, and that's why it's so because it's vented. And it's subject to ambient conditions outside, or the outside temperature and humidity, whatever's going on outside. is gonna be happening inside here and drafted through the ventilation process. And that's why it's so important to air seal this backside of this wall to get the optimal results.
Okay, wanna air seal that top side of that floor ceiling. You know how you said to insulate the wall?
Insulate the wall.
Okay, now take your floor joist and you need to seal that top of the floor joist across there. Keep it going.
Right here?
Nope.
Oh, no, actually, you don't need to do that.
You don't.
No. You do need to put a block here. You have to stop the air from coming inside our heated space. You need to air seal the top of the sheetrock here. And then you can put in on the horizontal. You don't have to put a 6-sided. You don't have to do that because the air will come through. It has the same effect, but that's not the practice. Like if you go up into attics, we don't put plywood over our insulation this way. So on the vertical, yes, 6-sided, and on roofs, 6-sided, but this could be blown with cellulose and it does not need to be covered. So it has to come all the way down here. This needs to be air sealed, the back side of the sheetrock. Then you can put insulation on top of it.
Okay, see that's a little confusing to me because you said the knee wall on the cold side was supposed to have sheetrock on it too.
Right there, right. Right there.
Right there, yes. So why doesn't the ceiling need it?
Why doesn't the ceiling need it?
Yeah. I mean, it's
You know, I don't.
same.
I'll take your name and number and I'll research it a little bit more. I mean, I knew at one point why, because I asked the same exact question, but I don't. I'll find out for you. I mean, I know
I
that
mean, it's the same space and.
it's not. It's actually it is the same space, yes, but it's not in one acid because we look at walls different than we look at attics. So this is considered an attic flat right here now. So we look at those differently. So as the way, and if I'm gonna take a stab at this, I might be wrong, but I'm gonna just think about it, think it through, is the way that everything moves is from high pressure to low pressure, high temperature to low temperature. So I'm gonna take a guess and say that because everything's sort of like a chimney effect and it's moving up towards this vent here that we don't necessarily need, or maybe it's because it's impractical. Here's another thought I just had, is typically, if this is a 2x8 floor joist,
Right.
we're going to insulate up well above this, 4 or 5 inches above this, so into 12, 13 inches, so we have continuous insulation on above the ceiling joist, which would make it impractical to plywood as well. But I'm gonna research that a little bit more, and if I can take your name at the end of the seminar, and I'll get you an answer. Or I'll get you a few answers.
Is the paper side of the insulation, is that considered the air seal?
Not by me, but
So if
It's
you're
cor-
insulating your roof up there that you would put the paper side
down to the heated space.
to the heated space.
So the vapor barrier would be the paper. The paper is called craft face, and that is a vapor barrier. If you think about how it gets installed, so
It's
each
not an air seal.
it is an air seal.
Oh,
It does air. It is an air seal, but it's also a vapor barrier, being less than 1 perm. So it can act as both. But practically, and if you think in the real world conditions, how would you possibly make that monolithic throughout a wall and seal it, unless you were to tape it all and be very, very diligent about making sure there's no penetrations in it?
Some salesmen tout the ability to put a reflective insulation in that space, like a sheet of aluminum foil or something to reflect the heat out. What's your opinion of putting that on both the knee wall and the attic side of the knee wall and the floor?
Okay. Well, the reflective barrier, I mean, I've seen studies showing that it can save a significant amount of money. But my question, I guess, is at what point when does it get installed? So if I come into your home today, or if we go into my house today, and I have a 60% efficient boiler, and I'm going to say, I'm going to save you 30% just by switching you out to a propane and 95% condensing boiler. So yes, that's going to save a lot of money. So if you go into a house that has no insulation, and it is, is extremely expensive to operate, and you put a reflective barrier in so that it bounces off and doesn't allow heat into the house, that's going to save money. But if we insulate properly, and address this in the steps that we're talking about, and then introduce a thermal barrier, or I'm sorry, yeah, a reflective barrier, I don't know the answer or how much it's going to save. You know, if we actually seal, where I would prefer would be actually to do is the an unvented roof assembly. So then, at that point, how much heat is actually getting through to reflect, and then how much work does it have to do to get back outside if we address the thermal envelope properly? So I don't know I haven't seen a study of that.
Okay.
You know, the salesman isn't going to show you that study. So I don't know if I don't know. Other questions?
One of the answers to your knee wall problem is, you're right, the lousy installation job of the insulation between the studs
Yep.
will give you lots of air spaces where you can get convection.
Yep.
The convection will rise up through the wall and strip the heat away.
Yep.
Then, as it molten in the floor.
I don't know. When you think about it, though, it's a loop, you know, so it raises it up, it hits this cold surface, it comes back down. It's gonna.
You could get the same lousy job on the floor, too.
Well, if you blow, yes, I suppose if it's fiberglass, you know, you're gonna have gaps and voids. But if no matter what, it's gonna create this loop like this, and it's gonna take some heat out of here. So it has me thinking a little bit. It has me thinking about this, and I'm gonna think about it and get back. Maybe, and this is a different space than actually in an attic. So you're going to have different results. So I'll find out.
Maybe, I don't think it would be.
Throw it out there.
It would be an expensive proposition to build a test house. Or,
Do you have any
No.
funds to?
do that.
Here's my card.
Yeah, it's,
We have done. We have been involved in we do build homes that I wouldn't say test homes, but we're doing a lot of cutting edge technology. We built last year. We built the house of the year for the Builders Association, or Builders and Remodelers. So what do we call that?
Builders and Remodelers Association of
Eastern Connecticut. Yes, we were the builders of that home, which was very different construction than is typical, and we're building 2 homes now that are very, very different than what's considered traditional. One has a double stagger stud wall, meaning it's 9.5 inches deep and it has a thermal break. And then the other home, which is in Preston, has 2 inches of foam on the outside, then 2x6 filled with cellulose. So we thought about, you know, the same thing, the vapor barrier. You have to let the moisture out. You know, no matter if it's going to get in, you need to be able to make sure it gets out. And both of those homes are heated with Mitsubishi mini splits, which I don't know if you're familiar with these ductless split systems, and then a little bit of circulation. So when you we'll get to that. I'm jumping ahead, but it is a different kind of technology. And we are doing things differently, and I wouldn't call it a test house. This is proven, but it's definitely different than the norm.
I have a question about the permeability of the insulation. Do you want a high number or a low? You listed some numbers, but I didn't know which one was preferable, or does it vary?
That's not permeable. That's the definition of a vapor barrier, which poly 6 mil poly or plastic sheathing is extremely impermeable. It's not an insulation. Some paints are very impermeable. And then high density foams, like rigid foams, are impermeable. So to answer your question, we're looking for a vapor retarder, not necessarily a vapor barrier. So we want high density, or I wouldn't say high density. We want insulations that are much less air permeable. I don't want to say a vapor retarder, but we want to. We definitely do not want air moving through our walls, because what happens is, and when you put in fiberglass insulation, if you think about your furnace, if you have a furnace, you change out the filter often. That's a fiberglass filter. So air moves very freely through fiberglass. Dense pack cellulose, not as much, but it depends on the installer. foam products, half-pound foam, which is called low-density foam, air moves through that, not as much as, nowhere near as much as fiberglass. And then you have what's called 2-pound or high-density foam, which air does not move through at all. It has closed cells. It's called closed-cell foam, so it doesn't move through it at all. So to answer, I hope I've answered your question, but to answer your question, we do not want air moving through our walls. So we want insulation and wall assemblies that are the least air permeable as possible.
I guess I was more concerned about moisture. And I know the air carries the moisture in, but if you want to be able to let the moisture out,
Yeah,
you need some permeability.
that's
So
kind of why I
the
danced around that. Yeah, it's the balance would be, okay, if you do not let moisture in. So if, let's say we built a home and we packed and we use all let's say half-pound foam, low density foam, and we filled it, the entire bed with that. So that is air permeable, but it's not. But it is an air seal. It's an air barrier. It's not a vapor barrier. But if you don't allow moisture in, so it's an air barrier. So if you don't allow air in, you're not letting moisture in. So and if you're not letting moisture in, you don't need to let moisture out. So yes, half-pound foam will dry seasonally in this temperate climate. Sometimes to the inside, sometimes to the outside. But you won't have a problem to begin with so long as it's constructed properly. And that's like a whole 3-hour conversation, which I'd be happy to talk to you about the way, because it's not just the insulation, it's the studs, it's the plastic, it's the sheetrock, it's the siding, it's the sheathing, the tape. You know, it goes all the way out. So there's probably 13 different layers that we need to consider when we're building these assemblies, and it can be a very lengthy conversation,
Thank you.
which I would love to have with you.
Yes.
Okay. And we're moving.
Maybe.
At some point, we will be moving. Oh, you know what? I better stop pointing if I turn that off. There we go. Okay, how do we test and find air infiltration in a home? Has anybody seen one of these before? It's a blower door. It's I have mine actually just behind that wall in my office. And what we do is this is a tool that we use that puts the house under negative pressure, pulls the air out of the house, and it gives on this, and this is called it's a DG700, it's a manometer. So it gives us, it has it has squirrels in there or something that do math, and they figure out how many CFM or cubic feet per minute, how leaky a house is. And then once it's under negative pressure, with an infrared camera or just walking around, we can find out where those leaks are, and then we can address those areas. And then from that number, how much leakage we have under certain conditions, we can figure out how much ventilation we need in addition to, because we need to have a healthy house. You seal up a house, you know, it can become unhealthy, and we're going to get to ventilation, so I don't want to jump ahead. Okay, this is this is going to take a little bit. This is a myth. I don't want to seal up my house too tight because it needs to breathe, and I've heard this a lot. But that's another $5 I would have if I had a nickel. But this is a picture of a house under negative pressure, and it's actually in a different state, and we'll talk about that. But see, the dryer. So if you think about a house under negative pressure, your dryer is removing the air from within your home and it's throwing it outside. Your bath fans, taking the air from your home, throwing it outside. Same thing in your kitchen. So it creates this negative pressure. And actually, that can be a way of having makeup air. So 1 unit out equals 1 unit in. So if you're putting 50 CFM outside, and someone opens a door or a window's cracked, or it's going to find its way in, you're going to get 50 CFM back in the house. But what happens is, I like this picture because it shows this, it kind of shows that the house is under negative pressure. One of the things, that can happen, if you hire someone to come in and say, I have no insulation in my walls, I don't want to do the energy audit, and just seal fix my attic, seal my attic up here and fill my walls in up this way because I'm paying too much in oil. But then you don't think about it, but you have there's different types of heating, but this is a natural draft boiler and a natural draft water heater here. So what can happen is you seal up the house. Now for years and years and years, your house has been leaking, and you're used to it, and your systems are used to it, so it hasn't been a problem. Then you seal up all the holes. You don't go through the process properly to go look at maybe some potential side effects, and this is exactly what we're talking about. So now this is under worst case conditions, so you turn all these fans on, and these are natural draft furnace. So this burns oil or gas, whatever, and it's open to the atmosphere and goes up the chimney. So now you turn this stuff on, and now this is what's called a condition called backdrafting. It's becoming less and less common as people are changing out because we don't use natural draft or natural draft combustion appliances much anymore. But there's still a lot of homes that have them that are being retrofit, and this is just one of the conditions that can happen. And to answer the myth, I don't need to seal up my house too tight because it needs to breathe. That's not true. You need to breathe and you need to live in a healthy environment, but your house really does not need to breathe. So we need to build tight and ventilate right is the way I was taught. So it's what happens is we need to, through the blower door, we figure out how much we build correctly. We use a blower door, find out how much leakage we have. Then we need to add in ventilation so that it not only goes out, but it also comes back in, so that you have a healthy environment. So you're not only just bringing in air from outside, which could be from near a combustion appliance, if this is sidewall vented. So you're bringing in air through a place that you don't want to bring air in through. So you want to bring in fresh air for the amount of occupants in it, for the size that you're in the home, and the amount of leakage that's. So it's a calculation. You want to control the amount of ventilation you have in your home so that it is healthy. That usually sparks questions, but I got one more for me. Okay, so we're going to move on to distribution, and this can be it's the way we deliver energy from various systems within our home to where we need it. When planning out distribution systems, minimizing friction or resistance is the key. A great analogy is offense versus defense. So, and we're going to talk about a couple different areas in distribution that are that I feel are the most important, which would be duct systems, and hot water. It also applies to electricity and a couple other different areas, but the most important, I would say, is a duct system, because we've up to this point we've talked about the buildings and possibly negative pressures, but actually the mechanical systems that we put inside, duct systems, distribution systems, they're the ones that those systems, when not designed properly, will cause the most problems. Okay, so these are some pictures of some bad ductwork. When it's not so good. So what we have is, we have these furnaces, and we think it's a 3-ton furnace. It's going to deliver 1,200 CFM or whatever it is, and we think that it's going to get to where it needs to go. But it's only as good as how it's installed. So this is obviously going to restrict flow to where it's going. So wherever that branch is going, it's not getting what it was intended to. And this here, I just think that's funny. I think there must have been a sale on flex duct or something. Bad ductwork continued, and you see this a lot, in older homes. This is wide open. So if this is a return, so a return would be taking air after it's heated, and it goes back to the furnace to be rewarmed and delivered through. So if this was in your basement or in your attic, and you had a moist basement, or you had, this is pulling air from an environment outside of what we've decided as we want to heat and cool. So you could be bringing mold, mildew into the home, and it also throws the pressure of the house off balance of what you would think. So this properly sized ducts and duct systems and distribution systems are designed, tested, and balanced. So this is the way that this is actually one of the homes that we did, and we do our own Rice-Off and duct designs. So we know how much, if this room needs 67 CFM or 150 CFM, we know what size this needs to be, we know what size all this needs to be, and it needs to be installed, per the best practices, and then we balance it at the end to make sure that there's the correct amount of airflow in each room for what it needs. Okay, domestic hot water. So this is I would say the second most important distribution. Hot water is, does anybody have a bathroom that takes like 7 minutes to get hot water? Yeah, we all do. And it's, what happens is, no? Well, that's good.
Hot water's off the burner, it's not a problem.
Hot water's off, so it's just right there when you turn it on? Oh, that's great. What happens is, a lot of times, we'll think about a ranch again, a 1950s ranch. I don't know why I like to use those all the time, but I do. So in the basement is the furnace all the way over to the left, because this particular ranch, when the builder built it, had a fireplace, and that's where the flue is. So in the basement, all the way over to the left, on the opposite side of the garage or whatever, is the furnace, and right off of that is the hot water heater. And they're both natural drafts. So it's going to be, let's say this ranch is 50 feet long, and you have a bathroom master suite on the other side of the house, way over on the other side of the house. So the hot water heater is over here, and it's running water, 30 feet to the kitchen, and 50 feet to the master bath, and 40 feet to the other bath. And the only reason is because that's where the chimney is. What in reality, or in best practices, we move that hot water heater. When we design a home and build a home or do a remodel, we think about, all right, so this is where we have the bathroom here. We try to keep them located. The kitchen's here, the bathroom's here, here's another bathroom. So we want to find a middle ground. So the shortest runs from each, so you have the shortest runs possible. And then we don't, this is actually called, this is daisy chain. So what happens is this is one line that goes up. It goes over, it tees, it goes over and gets this sink, it tees over and gets this one, it tees over and gets this one. We use manifold systems so that there's one singular line to each individual appliance. So it's the shortest run. It takes us the path of least, the least resistance of a straight line, or the shortest run is between 2 points of the straight line. So we try to get it as close as we can, and then we put the hot water heater as close as we can. If we can't do that, then we'll do a storage tank and circulate the water to it so it's closer, so it's close enough so that the shortest runs are possible. So that's something that if you think about your own home and, where's my hot water heater versus where, where your appliances are or your sinks and things like that. And then look at it and figure out why. Why did the guy put it here? Because it was convenient for him. Or if you have if it's an electric hot water heater, a lot of times some contractor might put an electric hot water heater closest to the electrical panel because the wire is expensive. But it might have only cost another $30, but it's going to cost you thousands and thousands over the years. Just something to consider. Okay, consumption equals bills, money. So we're going to talk about, there's two types, or the way I see it, there's two types of, well, there's all kinds of energy, but for this seminar and our purposes, we're going to talk about, there's two types of energy. Non-renewable is from an energy source used that cannot be recreated. So there would be natural resources, and we have renewable energy, which is an energy source that can be easily replenished, which actually can also include wood or recycled materials and things. Some fast-growing woods that are making pellet stoves, and some of that it's a very good argument for a renewable energy source. Okay, so now this is what a lot of people want to know about, and this is what this is what surprises a lot of people. Is all energy created equal? So some of you may use wood, heat your homes with wood. Some of you use propane. Number two, heating oil, electricity. So just so that we all understand, and this is you don't have to remember this, but because we're gonna elaborate on it in a couple more slides. Electricity. We need to take all of these different energy sources and compare them apples for apples, so that we can understand, what costs more, what uses more, what has the most impact on the environment. Electricity, 1 kilowatt hour, which is equal to a 100-watt light bulb on for 10 hours. So that's 1,000 consumed watts or watt hours is a kilowatt hour, and that's when you look at your electric bill. You're billed in kilowatt hours. So electricity, 1 kilowatt hour is 3,412 BTUs per hour. 1 gallon of propane is 91,000. I think 600 was listed. It's different in 2 different spots. 91,600 BTUs. Number 2, home heating oil. 1 gallon of number 2 is 100, and you'll find some different. It's 138,000 and 142,000, and that one therm is 100,000 BTUs. So that's it. That one's an easy one. Okay, so, and I actually didn't change it. Okay, this is based on 20 cents actually. I forgot to change that back. So now I want to explain this a little bit so you can follow along. The following is the market rate for 1 million BTUs of various energy sources. So it takes, now we're converting it into dollars. So apples for apples, we're converting it into dollars. And this is raw energy without efficiency even considered. We have to use it takes 293.1 kilowatt hours to have 1 million BTUs is equal to 293 kilowatt hours. 10.9 gallons of propane is a million BTUs. 7.194 or 7.2 gallons of number 2 heating oil. It takes 7 gallons to equal 1 million BTUs. And the easy one, 10 therms. So if you look at the prices here, you say, well, electricity is, everybody doesn't want to heat with electricity. It equals $58. Propane is $25. Heating oil is $25, and natural gas is $23. So these three, it looks like we should just, at this point, we should throw this out, and these are our options here. But now we're going to move on to efficiency. Okay. So this is actually, I wanted to insert a slide, but efficiency is output over input. So let's say we want to do, and it all has to do with what you intend to use it for. So we're going to talk about heating, but if an 86% efficient boiler, so how do I explain this? So I lost my train of thought. Anyway, I'm sorry. But
Every 100,000, you'll get 8,000.
600 back. Yep. Thank you. So if you put in 1,000, you're getting, or if you put in 100, you're getting You're only getting 86 for the use of what you intend for. Thank you. So we're going to compare the cost of 1 million. Just to add on 1 million BTUs to heat a home for the following: an 86% efficient oil boiler, 95% efficient propane boiler, 95% efficient gas boiler. This is just resistant electric baseboard, which no one wants. Now this is where it gets a little bit different, and I'm going to explain this. COP is a coefficient of performance. It's a term used in engineering a lot, and this is, if you think about that, what that is that's 450% efficient, using the same formula. So that brings electric back into the game. And then here, COP on ductless split, and the reason we're using this, I'm going to elaborate on this a little bit. Geothermal heating and cooling, what it is it's either vertical wells that go down into the ground, and it has a steady temperature of 55 degrees. So on one side of the refrigerant lines, it's always has a constant 55 degrees. So it's easy to calculate what it's going to cost for heating and cooling if it's engineered properly. A ductless mini split, this is an air source heat pump, which is the exact same technology, only it doesn't have wells, or it doesn't have horizontal loops. It's using the temperature outside and the humidity outside, whatever it is, to extract heat into a refrigerant line and deliver heat into your home. Like my house, is heated with a Mitsubishi mini split. I have a Hyperheat FE18, so it heats down to negative 13 degrees. It was 14 degrees at my house this morning, and I only have one 18 in my home, and it heats and cools the entire house. And when I installed that and got rid of my propane boiler, now my bills are, I also installed the air source heat pump water heater. My bills went from about 130 to 250 average a month, but I was paying several hundred a month in propane before. So, and what I'm doing is aligning myself and using my own 5-step process. We're going to be adding solar panels onto my house, which makes so I should be down to $30, $40 a month, all in, no fossil fuels. So the ductless split at 17 degrees, and why I say at 17 degrees is because the geothermal has a static temperature that you can go off of, so you can do, to make math easy. Well, the ductless split kind of throws a curve in there, so we have to say at what degree and an assumed relative humidity. Okay, so we're going to keep going. All right. That 86% oil boiler, with the cost of $3.52 for the oil, 1 million BTUs, will deliver, and the BTUs for that oil is 138, with an efficiency of 86%, now costs $29.66 for a million BTUs. The 95% propane, same thing, $2.30. 95% efficient is $26. Natural gas is a little bit less. If you have resistant electric, just electric heat, it costs $58.62. Geothermal, $13. And a heat pump at 17 degrees, and I could have added 5 or 6 more air source heat pump lines, because most of our heating degree days are well above 17 degrees. So this number would be, and that's why they don't rate them in efficiency, and I converted it to that, but it's $21. So this would actually look a little bit more attractive. So that's, so apples for apples, this is what we're paying.
Excuse me, I
Yep.
can't see that. I'm just wondering if you can just read out the different types in the final cost.
Just get, okay.
Yeah.
Get to the point, Andy, okay.
No, because I can't see it.
Okay. 86% efficient oil is $29.66.
Okay.
95% efficient propane, $26.43. 95% efficient natural gas is $24.53. 100% efficient resistant electric, just toaster, is $58.62. 4.5 COP, or 450% efficient geothermal, $13.03. And 2.77 efficient, 277% efficient air source heat pump, a ductless mini split, is $21.16. Now this is all assumed that everything's installed per best practices, like we talked about getting up to this point. This can cost a lot more if the propane burner isn't tuned right. If your oil boiler or oil furnace isn't cleaned and your filters aren't, you're not going to get anywhere near that as far as efficiency goes. Same thing with geothermal. The geothermal wells aren't installed properly, the duct system isn't done right, and you have electric backup. A lot of people have heard this a lot. I don't like geothermal because my bills are $800 a month. Well, you have a backup electric system, and it could be simply that the thermostat, someone's messing with the thermostat, and if it's more than 3 or 4 degrees off, it goes into backup heat, which is the same thing as this $53 or $58 here. So it's all in how it's installed and best practices. But I had to put a graph up, so that's what it is. Okay, so in summary, we want to minimize the amount of energy your house needs. So through insulation, air sealing, and also healthy home, as far as ventilation and moisture control, placing the proper insulation distribution systems, putting the water heaters in the right spots, et cetera, we can minimize the amount of energy that your house needs. And then we ensure that the energy that we do need is distributed throughout your home correctly, so that you're comfortable and you're maximizing your comfort and the efficiency of your systems. And I'm going to actually elaborate on this a little bit. In comfort is what drives heating and cooling costs. So if you feel uncomfortable, you're going to mess with it, and like I said, mess with the thermostat. So you're going to, cold and hot and this and that. And that is, most of the time, that is just a poorly designed and installed distribution system. It's not, and beyond the thermal envelope, but mostly it's a poorly designed and installed distribution system. So at a certain point, you have to select the energy sources that you want to utilize, so, and then because you have it's a map, you're drawing up to yourself a map. Like in my house, like I talked about, I switched over my heating to air source heat pump. I had propane, I had an on-demand propane water heater, which is in my basement, disconnected. I switched over to a heat pump, and now I'm going to be installing solar panels on my roof to make all of that energy on site. So I made a decision that this is the route I was going to go, and this is my end game. So I had to get myself aligned with it to capture and maximize my benefit for it. And then, like I said, select the energy sources you want to utilize, and select your mechanical equipment.
If your comfort level is 68 degrees, is it more efficient to turn the thermostat to 68 and leave it there? Or is it more efficient to turn the thermostat up and down?
It depends on what your heating system is. So if you have in a forced air system, or in a ducted system or ductless split system, it actually is better to have setback thermostats because it recovers very quickly. If you have it in geothermal, and if you have a geothermal system, it's kind of the set it and forget it thing with the chicken, but don't actually forget it because it might catch on fire. Same thing. Set it to where you want it at 68 degrees and leave it alone. Otherwise, the difference between what your house is and what you want it to be, you could set it back to 60, you come home and you want it at 68. In that instance, your electric backup's going to kick on and it's going to cost you way more than if you just left it alone at 68 degrees. Radiant heating and cooling, set it to where you want it and leave it alone. But if you have baseboard hot water hydronic system, you can set that back. That will recover very quickly as well. So it really depends on what kind of system you have. Yes?
1980s house, fairly new heating system. We have steam, the old.
I love that, yeah.
Yeah. What do you recommend then with that?
That recovers very quickly. It depends on if you have steam heat
Yes.
and you have to fill it with water, or is it now a hydronic loop where it goes one side and out the other, or is it go? Shh?
Or it's steam vented.
Yeah. Yeah, it'll recover very. I grew up in a house with steam heat. That's a very comforting sound to me. That might scare people, but I love it. That recovers very quickly. I would use a setback thermostat. It depends on what your house is too. Like for many years, my wife and I have a 7-year-old and a 9-year-old. They're not great people, but they're mine. They were home for they weren't in school for a long time. My wife was home with the kids, and so someone was always in my house 24 hours a day. There's no possible way, and now my wife's just finishing grad school, my kids are in 1st grade and 4th grade, and sometimes they're home and sometimes they're not. There's no thermostat in the world that we could program around our lifestyle. So we turn it down manually, and before, someone was always in my house, so there's no point in turning it down. But if you have a life where, every Monday through Friday, you get up, you go to school, or you get up, your kids go to school, or you go to work, everybody comes home at 5 o'clock, it's easy, on the weekend you want to sleep in, then yes, I would turn it down and turn it back up. But it depends on who's living in your home and what your lifestyle is. Any other questions? Okay, so this is end game here. Now we've made all these decisions, we've made the improvements, we started from square one, and said, okay, this is what our house is consuming, this is where we want to go, and now here's our energy profile, and now we're going to add alternative energy. There's a lot of different different options, but the number one that is used here mostly is photovoltaics. Mystic River is a PV, you might hear. We are a PV installer through CFIA, the Connecticut Energy Fund, Energy Efficiency Initiative Authority. So we are listed as a PV installer. Wind and water turbines is another option, but it's very, they're actually all three of them are very site specific. So if you don't have water, you're not going to put a water turbine in, and if there's no wind in your house, near your house, then it's not going to do much good. And if you don't have a south-facing roof and you have a huge canopy of trees, PV is really not an option for you either. So everything is really site-specific and needs to be evaluated. But once you, I'm not going to go into how photovoltaics work and all that stuff, but if you are interested, and if you, in your comments, if you want to write that you are interested in learning on how PV works, We can put together another seminar for another hour-long seminar about how that works and how you may qualify and how it might work for you, and what the terminology is, so you can become familiar with it. And then there's other alternative energy, which is solar hot water, solar air heating, which is kind of cool, and then there's other, evaporative cooling. There's all kinds of different things. And with that, I think my presentation is complete, and if you have any questions, I'd be happy to answer them.
Andy, could you elaborate a little bit on geothermal and how that works in relation to, comparison to the refrigerator, that sort of thing?
Oh, okay. A lot of people, I've heard a lot I've talked to a lot of confused customers regarding geothermal systems. And geothermal is really, it's not new technology. All it is if you have let me just think of the best way to put this. It's just a heat pump. And a heat pump, every single one of you have heat pumps, and you may not even know. Or your refrigerator is a heat pump. So my grandmother used to put socks behind the refrigerator because it would dry the socks. So, because what it's doing is refrigerators don't make cold, they remove heat through refrigeration, the vapor compression cycle. So at one point, we'll consider it a loop. No, I won't do it, but it's just considered a loop. At one place, it's actually taking heat, and in the other place, it's delivering heat. So it's not actually using the electricity to heat, well, electricity can't cool, but, well, it can, but that's a whole other conversation. But, so it's taking heat and moving it through different pressures of refrigerant and taking it and delivering it. And so if you have your refrigerator is taking the heat out of inside of your refrigerator and it's dumping it behind where the old refrigerators with the big coils, and that's how we would walk drying our socks. And that's the whole concept of air source heat pumps, geothermal. It's the same thing as an air conditioner. So if you were to, literally, if you know the box air conditioners that your wife says, please take the air conditioners out. You say, come on. So because no, I don't want to because it's going to dump water on my leg when I bring it inside the thing. That's the one I'm talking about. So you put that in. If you were to literally flip that around, and now you're standing outside, have your wife plug the thing in, turn it in. Now you got a heat pump. If you were to duct it, actually, so the vents were going back inside. So that's and that's the same exact technology as geothermal. It's just a heat pump. It has a valve. Because we can't actually change where the evaporator, where it's taking the heat from, and the condenser, where the heat is being delivered to, it has a biregular valve. So it actually just changes where it's taking and delivering. So it goes like this. That's a heat pump that also does air conditioning. So that might be a big aha moment for you. I don't know, but that's simply what geothermal is. So it's not so much, and I don't think of when we install geothermal or when we install air source heat pumps or when we install propane or natural gas. It really just boils down to, and I don't care what we're putting in. It starts with the process we started: the thermal envelope, moisture control, distribution system. So you can spend 30, 40, 50 grand on a geothermal system. If you have a crap duct system, you're going to be very unhappy with that you spent that money. And it's not the geothermal. The technology works. It works very well if it's installed properly. So, and it really, you have to have that. Remember that picture we had of the duct system? So you have to take that time, engineer it, think through it, think about where you need the heat, and if you take a moment, and we talked about heat quite a bit, but in this particular, or imagine yourself in your own home, or if you can't do that, think about this building right here. We have, below us, we have heated space. That's an outside wall. We have the roof here. That's our shop, which is like a garage, and that's an outside wall. So this is, this requires quite a bit of heat. But if you think about your bedroom, in your house, and let's say it's over a basement, which is, unintentionally conditioned, which is, for all intents and purposes, heated, and you have two walls, and there's bedrooms above you. So you have two walls in that one room. How much heat does that need? Nowhere near the amount that this room, or your second floor, which has 2 or 3 outside walls, and a roof. That needs a lot more. So that needs a lot more air, or a lot more heat, And it's all engineered and designed, and then it has to be tested and balanced to ensure, to make sure that you're comfortable in these spaces, and then you will have a good geothermal, air source heat pump, or propane experience. It's all driven by comfort. I hope I answered that question thoroughly.
Do you take into consideration the cost of those installs?
Sure, absolutely, that's why we,
Return?
yeah, and that's why I'm a HERS rater, so when we design and build homes, or when we do retrofits, that's one of the benefits, and the reason why I am a HERS rater is because what we can do is we can look at the amount of energy that is consumed, and then it has to make sense. So you look at the cost of the geothermal versus, and being a contractor, we know how much geothermal costs, and we know how much air source heat pumps cost, and we know how much propane, all these different things cost, and then the simple payback on them, and we can present that to our customers. But some people, and we started covering this at the beginning, but we talked about green. Now, it's different to everybody. Some people want, it's important to them to have less of an impact on the environment. So, for the same reason you buy, what's the return on investment on your granite countertops? Not that Michael would have worked just as well, but if that's what, each one of our customers are different, and every customer is different. Some people they don't actually care about the environment so much. They want to save money, and if we happen to, have less of an impact on the environment, that's fantastic. But other customers want to have less of an impact on the environment, and they're willing to pay for that upgrade.
What do you find the average life and or repair costs of, say, a geothermal?
Life and or repair, life, I'm only 35, so I don't know about life, but I know that I've been involved in the installation of 70 plus geothermal units, and they're very low maintenance. You have to have your contractor out once you get to check your pressures on your well side, as well as on your refrigerant side, and change your filters. So it costs much less to keep it running, but the initial investment is a lot more. Yeah, it is. What was the other side of your? Actually, you know what? I'm back up a little bit. The difference is substantial if you start at step 4. If you insulate, do your air sealing, make sure your windows, you just weather stripping or whatever, and then you go through the design process and you minimize the amount of, think about this. So if you go from 60,000 BTU design load, and when I say design load, what that is, okay, we want it 70 degrees inside and we're designing it to 6 degrees. So that's a delta of 64 degrees, a difference of 64 degrees that we have to make up. So now if we add insulation, we do this, we change the windows, we stop the air leaks, we stop the moisture and the decay, and now your heat load comes down to 30,000 or 25,000. We add foam and do siding, it comes down to 20,000. Now the wells, the biggest cost in geothermal versus a traditional system or a hydro air system is the wells. So what's the difference in a 60,000 BTU well or a 20,000 BTU well? It's 1/3. So it pays to go through the process. So the investment is still more, significantly more, but it's nowhere near what it is if you just go in and retrofit a house with geothermal.
I'm assuming that you don't necessarily recommend retrofitting the house with geothermal without addressing the envelope.
Absolutely, yeah, we won't. Yeah, it's just that it doesn't,
It's
customers
not
not
like
gonna be
new
happy.
construction, proper new construction, maybe I'd say.
Yeah, there's a series of steps, and we won't, because the customer's not gonna end up happy. You're still gonna have those drafts and you're gonna be uncomfortable.
So then, I'm a heating and air conditioning contractor, so
I can tell.
if we make an envelope, if we make a home that's properly insulated and sealed and all that kind of stuff, and we get down to a 20,000 BTU heat load, now if we look at a conventional heating system, if you will,
Yep.
oil, gas, whatever, versus geothermal, the cost difference of those installations and the return on investment. Comfort is no longer an issue because the envelope is what's made us comfortable.
Yep, correct.
Or, for the most part, I mean, obviously, distribution system, if you were talking about hydroware,
Yeah,
but
same
that's all
system.
gonna be the same, it's
All
all
the same,
gonna be the
yeah.
same, no matter what we're doing.
Mhm.
And now, as an example, say, that 86% oil have a 20-plus year life expectancy.
Yep.
And the geothermal same, we don't really do a lot of geothermal, so
Well,
it's
I
not a
was
trick
in-
question, it's a.
No, so I was in a house last week that had a 32-year-old geothermal system that was still going that I was looking at.
Really?
Yeah, I mean, it's in 32. I've looked at units as old as 35 years, and it wasn't working. We checked the temperatures, you know, we checked the coefficient of performance, the superheat on them, and because it was a hot water problem, but and they're still functioning very well. And we did this simple payback, and it did not make sense to change that heat pump out. So
So when you're doing the typical geothermal installation, what are you doing for domestic hot water?
it's case by case, really. You know, you can buy geothermal systems, you know, air to air, air to water, or you can buy them with these superheaters, and that you shouldn't rely on solely for your hot water. But there's a lot of different, there's a lot of different options. I mean, it's as versatile as anything else.
But in your experience, in your installs, what are they? Are they heat pump water heaters or are they electric water heaters?
Well, in my experience, because our heat loads are so small, and you can only buy down, you're gonna buy a 3-ton, heat pump, so that you're gonna have a lot of superheat. So we use that superheat because it's much cheaper at 4.5, at $13 per million BTUs. So we'll use that into an 80-gallon circulation tank, and then go off and then bump it with another tank. So you have a buffer tank and another tank. So we can capitalize on most of the hot water.
And of course, solar would be just like.
Solar's another way, but I mean, like you said before, solar hot water works. It works. You have to size it to the amount of gallons. Everybody uses like about. It's really, the spread is very large. So people use between 15 and 40 gallons per person a day of hot water at about 110, 120 degrees. So, and when you're sizing that for the winter time, when the sun is the lowest it can be, now flip the page and talk about July and August. How much hot water are you making in July and August if you're sizing it for the winter? I hope you have a pool, because you're making an awful lot of hot water, and it can become very, very hot, and you need a place to put this water. So I'm not a huge advocate for solar hot water systems. I think that money can be spent a lot better. But if like I said, people buy granite, because they want to, or some people want this. Solar air heating is another thing, which I find extremely interesting, and it works.
Any rebate programs for?
Oh, rebate programs. I'm sorry. I didn't know Enoch was not going to be here, but when the rebate programs, I'm actually not privy to exactly what it is yet, because it's being rolled out on the 5th, which is in a couple days. Yeah, so he was going to give an early preview today of what it is. But there is, for existing homes, I know that there's a rebate for mini split systems. I think it's I don't even want to say what I know what it was last year, $500 per system. I'm sorry, $300 per ductless heat system. Air source heat pump water heaters, I believe it was $500. That's for existing systems. And then there's rebates for natural gas, direct on-demand water heaters, and whatever. You can actually find all of this information out on desire.org, DSIRE.org. And then this week they'll be rolling out the new for the Energy Star. Well, I can speak about this. The Energy Star for New Homes program. So when you buy a refrigerator, and this thing might even be labeled Energy Star. Everybody knows it is. Oh no, that's not it. So your refrigerator has a sticker on it, it's blue, it says Energy Star. And that whole process, think about all the components made up of that refrigerator or a washing machine or whatever, has to follow the EPA's guidelines to meet Energy Star for that particular product. We happen to sell a product, a house, that has to meet specific criteria as well, as far as the air sealing of the home, the installation of the ductwork, the windows, everything has to meet a certain, then it has to be inspected and tested thoroughly, and there's rebates through CLMP, which is for meeting a certain HERS rating, which is a whole nother topic, but once you, HERS rating is a score of a house compared to the, a code compliant home. So if you, as you get lower and lower, like golf, the lower the score, the better. Same thing with HERS rating. So as you get lower and you meet the criteria, the incentives go up. You get a certain amount for being in tier 1, 2, 3, 4, and then advanced installation, you get more per square footage. And then there's, it goes on, and there's more and more incentives in the state of Connecticut. It's actually very worthwhile if you're going to build a new house to at least investigate and to find out if that's the type of home that you're looking for.
HERS,
HERS.
Okay.
It's the Home Energy Rating System.
Not his, hers.
HERS Index, it's called, INDEX. So it's a, and we can provide more information for you if you would like on that.
Excuse me one second, Andy. It's very similar to when you go to buy a new car and there's an estimated miles per gallon on the sticker on the vehicle. Probably in the next 2 to 3 years, you're going to find that every house that's on the market, including older homes that are going to be resold, you're going to need to disclose what your HERS rating is. So it's kind of, we're trying to establish HERS rating for each of our new homes. Once they've been completed, there's 2 different HERS ratings. There's one that's is it an assumed rating?
It's projected.
A projected
Or
rating.
plans based.
So when we design the house, we have a projected HERS rating we're trying to get to. And then once the house is built and it's tested, we'll know exactly what the HERS rating is. You're probably familiar with the word net zero, and a net zero home is a home that basically doesn't use any fossil fuel and has a zero cost of operation. So if you had a home that had a geothermal heating system, and in addition to that you added photovoltaic panels or solar panels up on the roof, the solar panels would create electricity to run the circulators to the geothermal, and basically that allows you to have a net zero home. Another way is, as Andy talked about with the Mitsubishi mini split, the air-based heat pump system is another way to do that without the geothermal, and with a very efficient heating system and a very efficient envelope. You have a much smaller heating system, costs less to operate by adding photovoltaic panels on the roof, assuming that you have southern exposure and limited tree canopy. Then you can create enough energy to offset the entire cost of running the Mitsubishi mini splits, the heat and cooling. So it's kind of, it all ties together. But the HERS rating is something that every one of us is going to know something about very soon. And those people that own the home that's built in 1840 that may have a HERS rating of 100 or more, it's going to be difficult to compete with a home that's newly built that has a HERS rating of 50. A home that is a code compliant home, Andy, correct me if I'm wrong, is about 80?
No, it's 100.
100? Okay. So in a new home built today, if you drive down the road to just about any subdivision, if it's a new home and it's not an Energy Star home, chances are the HERS rating is somewhere between 85 and 100. Whereas with some energy ceiling and even without the photovoltaic panels, you can basically, in a 2,000 square foot home, you can get down to around a 50 HERS rating.
We've gotten down to about 38, 40 without any alternative energy.
So that's a lot less energy consumption, a lot less heating and cooling load. So again, when we're comparing new homes to older homes that may be leaky, air leaks and so forth, and not well insulated. Right now when you go to sell a home, you're looking at or sell or buy a home, or let's say you're going to the bank and just trying to borrow money. They're looking at comps of comparable sales, comparable homes that have sold, and what the value of those homes were, how much they sold for. Those comparable rates or those rates are affected by foreclosures, by short sales, all of those things. So all of us have, anyone that owns a home has probably seen their property value over the last 5-6 years decreasing. So now we're going to add this other factor into it. As Andy explained with the heating and cooling, we looked at the cost of energy, and then we looked at the efficiency of the different types of heating systems. So now when you look at home values, once this HERS rating thing goes into effect and it's a requirement, you're gonna be adding kind of the efficiency factor into the comparable rate. So, you know, your home values, you know, could have a pretty big swing and a pretty big change once that becomes the normal process. So, something to be aware of.
I'm just curious, I know you did the house up on Griswold, on 138, a couple of years ago.
Yep.
And we've gone and looked at it when you had that first open house. And you had some pretty impressive numbers for that house, and estimated operating costs. And I'm wondering if there's any data for that.
I talked to, the guy that bought that house has become a very good friend of mine, and, because I live very close to that house as well, and, we're gonna be installing PV panels on his roof, and he paid, I actually just talked to him a couple days ago. His house is, I mean, through last week and no problems, and his average bill was 100 and something through the winter, like last month, I think it was close to 200, and that's, I mean, that's everything, all in, you know, that's, clothes washing, lights, heat, washer, dryer, heat, hot water, and there's 3 people living in that home. So, yeah, it's.
Yeah, I knew the numbers that you had projected then were pretty amazing, and I was curious as to how real world turned out.
It's right on.
Awesome.
It was, which is, you know, I was sweating a little bit, you know, but. Yes.
I have a question back to what you were saying about this rating that's gonna be coming out. We have a house that was built in 1929, so to extrapolate, what you're saying is, if we went through and we did this evaluation and upgraded and made our house more efficient, we'd be able to lower, and even though property values in our neighborhood of older homes are here, ours would be able to move up.
Right, I mean, when you're comparing one house that, let's say in new construction, if you're comparing a house that's 2 houses that look identical from the outside, one is Energy Star certified and the other one is not, so one has a lower HERS rating than the other. The one with the lower HERS rating is gonna have more value. Currently, actually, one of the houses that we're building now, one of the problems that builders are having today is with the comp rates when someone goes for financing. The bank basically does an appraisal of the house and the value of it. And it doesn't matter what it costs the builder to build it or how much the people are buying it for, the bank is only gonna loan you what they feel the value of the property is. So one thing that we found is that with the Energy Star homes, the appraisers are now starting to give that value. So the additional value is 9% is the cap, 9 or 10%.
It could be, yeah, it was.
Well, in the case of the house that we're doing in Preston, they increased the value of the house, the appraisal by 9% due to the fact that it was an Energy Star home, okay, without any photovoltaic panels. So there's definitely going to be additional value for those homes that are more energy efficient. Right? So when you're comparing older homes, the same thing is going to happen at some point, but you know when that date is or when that's going to happen, I don't know. There is no federal mandate that says on such and such a date we're going to be using that process. But some of the larger home builders in the country, you know, when you look at Toll and Pulte and Hovnanian, all of them are now using a HERS rating in all of their advertising. Okay, so it's something that you're going to see, you know, carrying on to everyone, even the small guys like ourselves. Does that answer your question?
Mm-hmm.
So the HERS rating is what, 2% of energy efficiency for a home house? And that takes into account what energy coming into the home?
A HERS rating is, what did it, I'll kind of walk you through it. A HERS rating is a score, is an index actually. A code compliant, a house that's built exactly to code compliant, which is called the comparing house, I can't remember the name of it, the reference home. The reference home is different for every house. So when I start entering data in that you have, you know, this wall south facing with this, which is built this way with X amount of windows and this wall, it builds a reference home which has a score of 100, an index of 100. So as we start adding more and more energy efficient measures or less and less energy efficient measures, so if I'm inputting in an existing home that has no insulation, the score can be up to 300. which is, consumes 3 times as much as a code compliant home, or in a new home or a retrofit, we want to get it down below 100, you know, being, if it's 50, it uses half of the amount of energy as a code compliant, or the reference home. So that's how a HERS index works, is we input all of the data, the efficiency of the boiler, the hot water heater, whatever it is, the air conditioning, the duct leakage, the air infiltration from the lower door, the orientation of the house being, you know, the front being north, south, east, or west, or whatever, the efficiency of the windows, all of the R value or U value of the doors, how many doors, the basement, if it has a walkout, is the you know, how high is the grade of outside of the house to the concrete, is that insulated, is it insulated underneath the slab in the basement, all of that, how big is the house, how much volume, you know, length, width, and height does the house have, how many people live there.
So it's all based on how well the house can maintain a temperature?
That's part of it, heating and cooling. Then there's the light fixtures. You know, are we using incandescent light fixtures? I mean, Thomas Edison, brilliant man, brilliant. But his light bulb is, I'm sorry, is outdated. You know, so we shouldn't be using incandescent light bulbs anymore. Compact fluorescents or LEDs, they use, you know, way more energy. So that's a factor in the HERS rating. The appliances, your washer and dryer, your refrigerator, and your dishwasher. How many kilowatt hours do they use a year? You know, or are they projected to use according to the EPA? So there's all of that goes into a HERS rating. Everything that you can possibly think of, we enter into the computer, and it spits out a score. And then from there we can make improvements to see it, and it also tells you on the right side of the screen, which I'm thinking as I'm doing it, on the right side of the screen, how much it costs per year, estimated with the amount of people living in it, and the area that it's in, you know, here in Connecticut or whatever, how much it costs for heating, cooling, hot water, and I can get a printout of everything, so as I make improvements, or let's say we're deciding that we're going to use this boiler or furnace or window, we change it out and say, oh, it's going to save this much money, and it costs this much more money or less money, so this is a smart thing to do, or the simple payback on this is just a little bit, is too long and really doesn't make sense. That's the advantage that we have at Mystic River that others don't have, is that we're able to make those assessments.
So with your standard 2,000 square foot home, what is the cost to drive the HERS rating from 100 down to 50?
It really, that's a very difficult question to answer, because it's kind of like saying how much is a car. You know, it's you know, there's a, you know,
Well, you obviously have to do the trade-offs for all those things. So,
yeah.
What does the house, with everything would being equal, is going to cost so many thousand or so many hundred per square foot? If you put all those energy things into it, how does it change the cost? You pick the ones that are the efficient for the year.
You know what? I can't. That's a real tough.
You want me to try that one?
Go ahead. Yeah.
Andy was thinking, I could hear the wheels turning there, but there's so many different inputs to it. But one of the things that Andy talked about earlier was that by tightening up the envelope, the heating and cooling system is smaller. Okay, so you're starting with a smaller equipment, which costs less to purchase and so forth. So really, when you take, all right, let's say that you went from a 2x4 wall construction home with 3.5-inch fiberglass insulation, you know, basically, you know, bare minimum. That actually wouldn't even meet code. So let's say a 6-inch wall with 6-inch fiberglass, and then you want to change that from 6-inch fiberglass to half-pound density foam. Okay, the difference in cost with that is probably maybe $3,000 or $4,000 more to do the foam. Okay, but if you have a savings by being able to use a smaller heating and cooling system, and instead of buying a boiler and duct system that costs $20,000 installed, and you're going to put in 2 Mitsubishi mini splits that are going to cost, let's say, $14,000, you just had a $6,000 savings there on the equipment side. So therefore,
Energy Star rebates.
all of these things, they kind of, you know, outweigh.
Yeah, but you've never been curious enough to do the numbers if you built 2 houses side by side, how you're going to come out,
Oh, yeah,
apply
absolutely.
all your expertise
Yeah,
and
absolutely.
get a cost per square foot. So I'm
Cost per
just saying,
square foot.
how big's the difference?
it's, we can, it can be that, we can make it the same, or most of the same, for the way we build. So like Norm was saying, if we trade off, if we increase the walls, and then we're able to down and save we need to save money, we need to grab a big chunk, and that's usually out of HVAC with the smaller heating systems having air conditioning and heating. And then if you can get some significant savings from Energy Star, or from CLMP through the Energy Star program, you can be about the same cost per square foot. But cost per square, I would need to have, a subdivision with 30 or 40 lots in it, so I could answer that question for you, because land costs more, the site work is different, it really is, and it's the customers' selections as well. So how much does it cost per square foot? I don't have an answer. I don't have an answer for that question. But what I can tell you is, we can get it to very close to comparable to the standard build of the way we build anyway.
You could say that it would be in a $250,000 or $300,000 home, it's probably less than $5,000. Okay? And the energy savings that you would have over time would by far outweigh that. So when we look at building a home to meet Energy Star standards or not, the payback period is very minimal. I'd venture to say that if you're going to stay in the home for 5 to 6 years, easily pay for itself.
That's kind of how I felt. I wasn't going to say that.
So, and one thing about the geothermal side, when you're thinking about a geothermal system, that I know someone had asked the question, what does a geothermal system cost? And again, it depends on the depth of the wells, the size of the home, and all of those things. But for a quick comparison, a hydroware heating system is probably, for a 2,000 square foot home, could be $18,000 to $20,000. Geothermal could be about 30, right? If you have the geothermal for 30, and then you put another $20,000 worth of photovoltaic panels on the roof, you may be able to get $10,000, $12,000 worth of rebates to offset some of that cost. So now you have maybe a $35,000 or $40,000 heating system versus 20, and the difference is
30% rebate.
Right. Yeah. So you have the different rebates, and then it really depends on how long you're going to stay there. So if you're building a summer home, a Long Point, that you're planning on turning over to your kids down the road, if you put in the geothermal system, they'll thank you for it when the heating oil is $8 a gallon, 20 years from now, or 10 years from now, maybe even next year.
Yeah.
Right. But if you're planning on building a house and you're thinking that, I'm going to build a house and in 5 years I'm moving to Florida or moving to Arizona or something, I would say I would go with the Energy Star and probably skip the geothermal system.
It is by case basis. I mean, we haven't built a home that has, oh no, that's not necessarily true, but we haven't built many homes that have fossil fuels in the last few years, at all. Just because the uncertainty, of the cost of oil and propane and natural gas. There's some places where there's natural gas rebuild, but mostly where we find is, there isn't natural gas run there, so we try to stay away from it as much as possible. Yeah.
You didn't mention anything about solar heating.
I'm
sorry.
Yeah, no problem.
Continue the question of estimated costs that you're having trouble answering, but in a different piece. The evaluation again of my 80-year-old home to look at efficiency and what we need to do to make it better. What would you project for something like that? Or, anybody's standard to have a 100,000 foot home or whatever it is, your 2,000 foot home that you're talking about. What is the cost of that evaluation?
The cost to do an evaluation?
The cost to do the evaluation of a pre-existing home.
We have to talk after. I have to get more information as to where you are, what you want done, what kind of report you're looking for, what kind of services you're looking for. It's kind of a case by case. We're not an energy auditing company. We do some energy audits, but where some companies have $400 for a complete energy audit, this is the package with the report, this, that, the other thing. It's kind of a case by case basis for us. So it depends.
We're happy to talk to you about it. if you'd like to.
Okay, he showed in his slide presentation where they were doing that, and that's where you needed to start with a pre-existing home.
Yep.
Of evaluating what you have, so I presumed you would have a idea of what that would cost.
It could, it's between $300 and $500 usually. You can get an energy audit from, CLMP, what's the name of that? Is that $75 audit that they have?
CLMP.
It's through CLMP, but it's called something, it's
Home Energy Solutions Program.
the HES program, yeah. They have that, you can call, and they'll come in and they'll do some air sealing and get your, they'll do some different stuff, but they're not gonna give you a comprehensive roadmap as to where you want to start here and go there. So that would be like a very comprehensive audit that, takes quite a bit of time, and that's when we sit down and really, you have input into it, a lot of input as to, this is where I am, and this is where I want to go. So then we start, making a plan from point A to point B, to where you want to get to. So that is, it varies customer by customer, as to how much involvement or how much time it takes us to do that. Yes?
What is your opinion of party plans?
I like party plan.
Thank you.
Yeah, it's got a, party plan comes with a 15-year warranty. It's got, 2 coats of like a baked enamel finish. It's made out of a high content of recycled concrete. So we use a lot of it, and it's durable, it's proven, and we've used quite a bit of it.
What was that in reference to?
Hardy plank, siding, H-A-R-D-I, hardy plank.
Hey, great presentation.
Thank you.
Yeah.
I don't know, I don't know. Well, thank you for coming, if you want to,